One more smart. Wait. All right, so we're going to talk about ion-selective electrodes. As I said, I don't have a clue why it's in this chapter. It's a bit baffling to me, but I wanted to talk about these. We'll talk about. All right, so one thing that this kind of brings up is the fact there can be a potential difference just because of a phase boundary. Where do we see this in electronics? Anyone remember any example in electronics where we just actually things together and there's a potential difference? Semiconductors, and that device is called a transistor diode. Diode is 2, transistor is 3. Right, so, just by putting two semiconductor types of semiconductors together, you can get a potential. Same thing happens here. If it's not free for things to move really easily, you can get a potential difference just due to kind of like two solutions, two electrolytes. Right, and if you gave it long enough, right, if you just had two solutions of two electrolytes, right, they would mix until the electrolytes were equal. And as I said, depending on how they mix, if you put in something that was like, if you like sodium chloride, it may not be a big deal. But if you have put in something else that's like slow moving, as they sort of mix, you may end up with charge imbalances. You may end up having more positives over here than over there, and that's again, potential. My favorite definition is work done to separate charges. So if your charges aren't exactly equal, you've separated them. You had to do some work to do that. That's why a voltage comes up. So if you got charge separated, meaning your electrolyte, your charges aren't the same kind of throughout. So you put them together there. And so when people think about this, they'll sometimes call it like a liquid junction or something like that. And again, we don't think about this too much in our work. But again, any place you have a junction, you could have a small potential difference in flow. Just from things kind of sort of being non-equal. All right, for them to equal out, we need charges to move. And so charges move based on their transference number. So there's kind of a T that tells you how fast they move. So that tells you about how things move. Remember, though, that we're also thinking about the fact that they're actually moving through an electric field. So I punted all of the mass transfer stuff till tomorrow. But movement in an electric field is called migration. I haven't mentioned that word yet. You're talking diffusion. I've mentioned that word, where things just move according to the concentration gradient. Migration is when things move according to charge. And again, you may hear me eventually and be mean and group meaning and correct somebody. When you talk capillary electrophoresis, we should be using the word migration. So you talk about migration times rather than retention times. So migration, again, because it's moving in an electric field. So the word migration has to do with an electric field. And again, anything that moves, right, is going to want to go one place, but it's going to experience drag. Right, so we've always got this friction to be able to move as it's trying to move, right, due to the electric force that's kind of pulling it to where it wants to be. And so usually the transference number often depends then on the radius, because how much drag you see, how much friction you get in the solution, right? It's going to depend on how big you are. But you have to remember that the radius includes the radius of hydration. So sometimes people will look at something like sodium or something and say, but it's small, why does it go slow? Well, that's because it's real hydrated, it has a lot of water around it, it's untracked. So it's not quite as what kind of goes. And so it just depends on That's kind of like liquid-liquid junctions against, I'm talking about too much. But this is where, again, the electrolyte kind of comes in and what kind of ions you want, depending on how fast they're going to move around. Okay, so what I really want to talk about are glass electrodes. All right, so I want to talk about glass electrodes. Number one, because those are our pH electrodes. Number two, they're also used as in a whole class of other type of electrodes. So typically, we would write out the electrochemical cell, and we don't have to memorize this, but this might be one. This is the electrochemical cell for a saturated calomel electrode, which again is not, as I said, there's practically only two reference electrodes that anybody ever uses. One is silver chloride, the other one is mercury-based saturated calomel electrode. So that's a calomel electrode. And that's in boundary then with your test solution. So again, we're going to measure pH, right? This is your pH. Whatever solution you feel like pH. And then that's in boundary with a glass membrane, and on the other side of that, you usually have some sort of silver chloride. Internal reference. So this is all inside your pH meter. How many electrodes are in your pH meter? 2. Right? That's really confusing to people because they plop one thing in there. But almost all commercial probes have an internal reference, right? We can't get around the fact that we have to have 2 electrodes to measure voltage. We still have 2 electrodes just because if you only put one thing in doesn't mean it wasn't there. So the one is internal to the other one. And then they're separated by glass. You have glass, that's in the middle, and this dry glass has ions in it that can move around, often lithium, maybe some sodium. And then over here we have some sort of hydrated glass. Right, so this is the part that gets wet. And again, we can exchange ions of hydrogen in here for sodium or lithium there, and those will go in there. And then on the other side, with our test solution, it sits out here. Right, we have our internal reference solution on the other side. Usually it's some sort of like HCl again, and you have your silver chloride reference sitting in again, this is hydrated. And it too can exchange with this. And this, of course, is a known. So ions can move through this dry glass. But is it easy to get something to move through glass? No, right? So this is very highly resistant. Like, I think some on the order of like maybe 10 to the 9 millimeters. Extremely highly resistant to get stuff to move through. And so we end up getting a potential difference. Between these 2 places, between this membrane and that membrane, again, which we can look at as far as that internal standard goes. All right, so it turns out that I told you we could exchange hydrogen over here for the salts that are in the glass. Turns out that you can get a little bit of response sometimes of a pH electrode to sodium, and it's often called the alkaline error, which tells you that often if you're a really high pH, it will also respond to sodium. It has to do with the type of glass. And you get to a really high pH, that it can respond as well to the glass. And basically, we would write out the Nernst potential for this. Some sort of constant, E0, RT over NF. And so what you would end up getting is the activity coefficient of H plus some sort of selectivity factor for H plus over Na times whatever the activity of the Na plus. This is a selectivity factor. And most of the time it's very highly selective. That is, but it responds much more hydrogen than sodium, but at high pHs. Again, I mean, even though the highest anyone ever really perspective is like 10, I think that's not really too much to worry about, but almost all of the other ions are less than that. It's really, really bad for hydrogen ions. Those are hard to exchange. And so, again, it follows the Nernst equation. It's just that your lovely, PhD here does the calculation. A year ago, I did an ion-selective electrode experiment with my class. We did a fired electrode. When I went to buy the meter, there's actually meters you can buy, just like a pH meter that do all the calculations. And I was like, no. So I didn't buy any special meters. I made them actually read about millivolts, like the change, and then do the calibration plots, and actually calculate themselves as far as that goes. I guess, again, it can't hurt to draw the structure of glass. Again, if you ever take separations, you need to know this. This is capillary electrophoresis too. That we kind of have a side roof lattice, and that usually this has somewhat of a negative charge, right? So that's when we have cations, we kind of offset. So this is there's a lattice. We can have these negatively charged things. And again, with capillary electrophoresis, we talk about the same thing. It's about that the walls of the capillary are negatively charged. Product of the glass. Okay, so if you can make a glass electrode, you can do way more than just sense pH. So it turned out that all of the first gas sense electrodes worked on much the same sort of thought. That you would have like a glass pH electrode, and then you would put on it some sort of polymer usually. That would like allow your gas through, that kind of thing. And when it would get in there, you would have something you would react with to cause a pH change. So CO2 is really easy to think of, bicarbonate, the whole sort of thing. And so you could cause a pH change. And then relate that back to the amount of gas. And so there's something in that polymer, again, some sort of electrolyte to react with. And so this was done for sp3, CO2, ammonia, that kind of thing. So again, you can play that trick of looking for those sorts of things. Another type of electrode that I just want to mention, because again, everybody thinks you know this. And that's the Clark electrode. So if anyone says, oh, it's just like a Clark electrode, again, I want anyone to be like, Clark electrode, what's that? It's like a total electrochemical fail on your part. Everybody thinks you know what the Clark electrode is, and what it is an oxygen sensing electrode. And so basically, again, it's an electrode with a membrane on the surface. In this case, though, oxygen diffuses in, it gets trapped, and then they directly detect oxygen. So they'll do a reduction. Again, I will read papers still today where they're like, design a Clark-like electrode. You know, something like that. It clues you in that they should be looking at that. Most of the time, these are platinum. This would be like a platinum electrode, but not always. And so people think that, again, I just want you to know Clark electrodes are for oxygen. And if you start, anyone starts talking about that, then oxygen should just drop into your brain. All right, the last type of ion-selective electrode. Is an enzyme electrode. And so you can do this with BH, but you don't have to. So what they do is they'll take an electrode and they'll put some sort of polymer on it, and in the polymer they'll trap your enzyme. Right, and so when the molecule that you want to see comes in, right, the enzyme will convert it to something else, like Y. And then Y redetect. So, you can do this with the H electrode as long as this was like X goes to Y plus H plus, you know, like if you were to lose or gain an H. And there's a lot of reactions that actually do that, acetyl and esterase, acetylase. I don't know how to list them. There's a lot that will do it. That you know, either consume or produce, you don't really care which one, an H plus, and so you can detect things like that. Or Y could be something that you could just detect electrochemistry. So the ones that our lab is more familiar with, oftentimes Y is in H2O or anything. So that's something you can detect electrochemically. All of the adenosine ATP sensors get you the hydrogen peroxide. So again, if you ever read papers and you're like, why do people care so much about hydrogen peroxide? You know, like who really wants to detect that? The answer is because if you can get to hydrogen peroxide, there are a whole lot of things you can make an enzyme sensor about. A whole lot of things that you can kind of do with that. And so it's in this section next to the pH electrodes, but it doesn't have to be a pH electrode, it could be a direct detection of water. Okay, so we'll just finish there. Tomorrow we're going to do chapter 3. So we're talking about kinetics. We do a little bit on mass transfer, because that's chapter 4, but I'm hoping to spend at least half the time on chapter 5. So we're going to race through 3. That's a lot of time there. We're going to do the briefest stuff on 4, and then we'll do it.